It's pretty much like when we made the alkoxide anion when we were doing the Williamson ether synthesis. Really, the alkoxide really wasn't used for anything other than doing that reaction, and the same thing's true here. When we make the acetylide anion, really the only reason we make that is to undergo the substitution reaction. So in general, we call these things alkylation. So when we're adding on an R group or an alkyl group, that just means some carbons with hydrogens. If we were adding on that group, it's called an alkyl group or an alkylation. And really, that's the only reason why we make the acetylide anion is to do a subsequent SN2 reaction and put an R group onto the end of our terminal alkyne here. So this is the idea. This is the first step in the reaction, but I also want you to understand that once we make this, we tend to undergo the SN2 reaction. So here's the other part. So there's two different pieces in this overall reaction sequence. I want you to understand what's going on in both of them. And then here in a second, we're going to put them all together into one step, which is typically how you see this. But in the second step, after we form the acetylide anion, we do the SN2 reaction. And then I just remember that, I kick off my leaving group and I replace, whatever alkyl group, this ethyl group here, whatever alkyl group comes off of the end of my terminal alkyne here. So this ethyl group is attached to my alkyne. We lose the negative charge, we lose the leaving group. And so all I really need to do is put a line and put CH2, CH3 there. And so remember, we showed this other piece of my alkyne as being an R group. That means that there's really, no difference in variability there. That I can put pretty much whatever I want coming off of this into my alkyne, and it will carry through the reaction. And really, when I look at these products, I just kind of draw this part of the reactant, and then I change the part of the molecule that's actually undergoing the reaction. So here I just copy this part down, get to here, and then I say what's coming off of my nucleophilic carbon, draw a line for the bond, and then I say whatever alkyl group's coming off my halogen, CH2, CH3, and that's how you get to the product. So the idea here is we typically combine these two reactions together because there's really not a lot of use in the world for the acetylide anion other than doing the SN2 reaction. So very similar to when we were talking about the Williamson ether synthesis, we put both of these reactions into one sort of step. The idea is we're not stopping after the first step. So that's what the 1 and the 2 means. We're doing a deprotonation here and then an SN2 reaction here. And we typically combine the two steps together. And this is how you'll see it a lot of the times, but remember, I want you to understand what happens after the first step, what happens after the second step. But when I see this, I start with alkyne. I see now sodium amide, a halogen. I'm knowing I'm doing an alkylation. And really all you have to do is remove this hydrogen and then say whatever alkyl group is coming off of my halogen, that's going to take its place. And the same thing, whatever's coming off the other end of the alkyne, it doesn't matter. I could have 1 carbon, 5 carbons. I just say what's coming off of that. Okay, CH2, CH3, I copy that down. Then I say this other carbon is going to get whatever alkyl group is attached to my halogen here. So I remove the hydrogen. Okay, this has got a CH3. Well, that CH3 is coming off the other end of my alkyne. I've drawn the product. So how do we form an alkyne? So we talked quite a bit about forming alkenes, and remember we can make that from elimination reactions, E1 or E2, but typically when you make an alkene you use an E2 reaction. But we haven't talked about alkynes and how do we do that, and we are going to make an alkyne very much the same way as we made alkenes, just we're going to do it twice, and because we're doing it twice we need a stronger base. So when we made an alkene back in the last exam material, we were able to use like hydroxide or alkoxide, a weaker base. But now the reaction is going to be a little bit more difficult. We need a stronger base, and we've already talked about our strong base, which is sodium amide. So we use sodium amide as the base that we use to make alkynes now. And really what we do is we do an elimination reaction, but we do it twice. So when we talk about elimination reactions, and this is actually an E2 reaction, when I say an E2 reaction, remember I kick off a leaving group, I kick off an adjacent hydrogen, I form a double bond. And so now we're doing this twice. To make an alkyne, you need two carbons adjacent to each other, both with a halogen, like a bromine. And so we're going to do this elimination reaction twice. So we need the stronger base, so we need sodium amide. And literally this reaction goes through 2 eliminations. So when we start the first one here, I'm kicking off, this leaving group and this adjacent hydrogen. So remember, this hydrogen is adjacent to this leaving group or halogen. So I kick off this one, I kick off that one. I draw a double bond across there, so we still have 1 hydrogen left over, and we still have an adjacent hydrogen. So this is where it gets a little tricky. Now we're trying to do an E2 reaction on something that already has a double bond, and that's why we need the sodium amide here. But sodium amide comes in and does the same thing. So we kick out the leaving group, we kick out an adjacent hydrogen, and then we draw in this case, a multiple bond. So now we've made an alkyne. So we just did an E2 reaction. All we did was do it twice. Every time we kick out a leaving group and adjacent hydrogen, we make a pi bond there, a multiple bond. And all we have to do is do it twice. So we need the 2 carbons adjacent to each other with halogens on it. And so this actually follows an E2 mechanism. And the idea is we don't need to rediscuss that. We've already talked about the E2 mechanism. If you need to understand it, you can go and look at it. But here, really what we're worried about is what can I do to my alkynes, or how do I make alkynes? That's really what we're focusing on. It's not so much the mechanism in this case. So really up here, I broke it up into 2 steps so you can really see what's going on. But this is how it will look if we want to actually draw out the synthesis of an alkyne. That will just show our starting material, our 2 halogens. And now we need 2 amides, and we'll talk about this a little bit more. Sometimes they'll put a 2 out in front of the reagent to imply that I actually need 2 of these. So for every one of these molecules, I need 2 sodium amide molecules for this reaction to occur, and that's kind of important. So the idea is if I need 1 mole of this, I need 2 moles of that. And sometimes they will show that by putting a 2 out in front of the reagent. But overall, it's a double elimination. I'd say, well, I kick out 1 leaving group, 1 hydrogen, draw a double bond, kick out the other leaving group, the other adjacent hydrogen, I draw a double bond across there, I make an alkyne. So this is how you'll actually see it. You won't see it broken up into individual steps. But we wanted to look at that to understand that we literally go through 2 eliminations to make an alkyne. So some of the things that we can do, so we're going to go back through and do some of the reactions that we did to alkenes, and they're going to look pretty similar, but the idea is with an alkyne, we're going to have that second multiple bond, and that's going to change our products a little bit. So when we were talking about alkenes, we talked about adding in an alcohol or turning an alkene into an alcohol, and we also talked about putting that OH for the alcohol, Markovnikov and anti-Markovnikov. So the Markovnikov one was hydration. The anti-Markovnikov was hydroboration. And so we're going to see those 2 reactions again in here in just a second. And we're going to start out with the OH. But the fact that after we form the OH inside of an alkyne, there's going to be another multiple bond in there, that's going to change our product a little bit. But the idea is the look of the reactions are going to be pretty similar. And hopefully that'll help you remember what the products are. So look for similarities and differences. So it's kind of similar in where we put the OHs. The end products are going to be a little bit different. So the idea is it's going to undergo a process called tautomerization. So don't worry about that. Next semester we're going to talk a lot about tautomerization. So it's just a word right now. It means kind of a fancy rearrangement. We'll go into this in detail in 335B. But the idea is instead of making an OH, what we're going to end up forming is a carbonyl or a C double bond O. So that extra double bond that was on my alkyne is going to be shifted to the oxygen. And depending on whether we do a Markovnikov addition or an anti-Markovnikov addition to our triple bond, we're either going to form a ketone or an aldehyde. So it's not going to be an OH, it's going to be an oxygen with a double bond. That's the big difference. And that kind of makes sense. A triple bond, an alkyne has got an extra multiple bond, and so now my product has that extra multiple bond. And so that is actually literally what happens. So we'll take a look at that. But we can still have Markovnikov addition and anti-Markovnikov addition to an alkyne. We'll explain that here in just a second. And remember, the species that do this are going to look pretty similar to when we were using a triple bond, but there's going to be a little slight difference. So with the first one, if I want to add an OH to my triple bond here, following Markov-Nikov addition, I still use my water and H2SO4, but remember with alkynes, it's very similar to alkenes, but it needs a little extra push to it sometimes. So the reagents, they're going to look similar, but they're a little bit different. And because this is a little bit harder than normal, we have to add mercury, Hg2+, inside of there to promote this reaction. So it still has water, it still has H2SO4, but we're actually putting mercury inside of there. And we've already kind of seen this mechanism. So the mechanism of that is the same as when we were talking about alkene. But overall, what we end up doing is adding our nucleophile to the more substituted side. And with a triple bond, it's kind of easy to find the more and less substituted side because one will have an R group and the other one will not. So the one with the R group is the more substituted side, and the one with the hydrogen is the less substituted side. So there is still a difference. We can still get Markov-Nikov and anti-Markov-Nikov addition to a triple bond. Markov-Nikov addition means it's going to go on the carbon that's attached to my alkyl group. Anti-Markov-Nikov means it's going to go on the carbon that is initially attached to my hydrogen. So after we do Markov-Nikov addition, remember we're still using water as a nucleophile. Neutral nucleophiles lose the hydrogen. So in at least the first step, I break the double bond, I form two single bonds. The more substituted carbon gets my nucleophile, so it gets the OH. The other carbon in my triple bond gets a hydrogen, so we go from CH to CH2. And then we stop at this intermediate. And so this is what the brackets mean whenever you see this. It means we make this, but it doesn't stick around. It means it's transitory. It means it's going to turn into something else. But we do form this species for a moment. And the idea is, and like I said, we'll talk about this more next semester, it is actually more stable for the double bond to be on the oxygen. So the C double bond O is a more stable bond than the C double bond C. So it's kind of thermodynamically favorable for this molecule to rearrange. And so with this, really all you need to know is this hydrogen jumps down to this carbon and the double bond jumps between the carbon and the oxygen. So here, instead of OH, we have C double bond O, and then this carbon, which has two hydrogens, gains the hydrogen from the oxygen. It becomes a CH3. So this is just looking at it in terms of making sure you understand what's going on. But really what we want to focus on is how do we do this? How do we do this? And more importantly, how do I go from reactants to products? So right now, mostly what we're focusing on is drawing the products. So just to show you a little bit more of what happens here, how do I make this conversion from this species with an alcohol to this species with in this case, a ketone? So in the first step, we still do electrophilic attack. So this is the mechanism for doing that conversion. So we still have this intermediate, has an OH and an alkene. Alkenes are susceptible to electrophilic attack, and so because we have acid inside of our reaction, there's still a lot of H+ roaming around. Here, the double bond attacks H+. H+ is an electrophile, so we put this hydrogen on the carbon without the alcohol, and that puts a positive charge on the carbon with the alcohol. So here now, and this is a little tricky to see, when you have a positively charged carbon, a carbocation next to an oxygen, there's this special resonance structure that you can draw that stabilizes this carbocation. And we're going to see this a few times, so it's an important part of organic chemistry. We put the carbocation next to an oxygen, and the reason why is the lone pair electrons from the oxygen can drop down, form a double bond, and get rid of the carbocation. So the positive charge gets moved to the oxygen. And so this is one of my favorite questions when we talk about this in class, between these two resonance structures. And literally all we've done is just move these electrons down to form a bond between the carbon and the oxygen. Remember, lone pair electrons attacking a bond forms a bond. So we go from a single bond to a double bond. We lose these lone pair electrons, and then now this positive charge jumps to the oxygen. When we're looking at these two resonance structures, I say, which one is more stable of the two? And it's very common to say, this one, because the positive charge is on the more or the least electronegative element. But that's not true. Remember, the first rule in stability in organic chemistry is the octet rule. So if the octet is violated, as far as I know, there's nothing that can beat that. The least stable thing is the one with the violated octet. So between these two, this is the big difference. This carbon has a violated octet. And I think that whenever I see a carbocation, I think violated octet. But with the adjacent oxygen, we draw this resonance structure that puts the positive charge on the oxygen. Now in this product, we have full octets. So now my carbon has got 4 bonds. My oxygen has got 3 bonds and a set of lone pair electrons and a positive charge. It's not happy, but it doesn't have a violated octet. So here we had a violated octet. Here we don't. So the oxygen and the carbon both have full octets. So this resonance structure is much more stable. So this is something we're going to see a few times. Putting a carbocation next to an oxygen is very stabilizing. So now when we have a positively charged oxygen, so we've seen this when we were looking at neutral nucleophiles a lot of times. Oxygen, has a full octet, but it doesn't like having a positive charge. If we want to get rid of that positive charge, the easiest thing is to just give it to a hydrogen. So we undergo a deprotonation, and now we are at our carbonyl here. So the mechanism's nice, but really what we want to consider is how do I go from reactants to products? Remember, that's going to be one of your more important ideas when you're studying for this exam. You want flashcards where you have the reactant and the reagent on one side of the card. You flip it over, there's the product. That's still going to be one of the primary things that we look at inside of organic chemistry. Still, it's the reagent that tells me what's going on. So here we're starting with a triple bond. The reagent tells me that I'm going to be adding oxygen to it. Remember the water and the H2SO4, that means we are going to be adding an oxygen Markovnikov. So in between these two carbons inside of my triple bond, this is the more substituted one. So this is the one that's going to get the double bond. And so here it's not so pretty. You need to remember, and we'll keep track of the carbons. Basically, you break both of these double bonds and you form 4 sigma bonds. So you break 2 bonds and you form 4 bonds, 2 new bonds on each carbon inside of there. So that makes sense. I'm breaking 2 bonds here, so each carbon needs to gain 2 bonds. And so the idea is, well, what do those 2 bonds go to? So the carbon that is more substituted, those 2 bonds just get shifted to an oxygen. So I get rid of the 2 bonds here. Remember, there's going to be a single bond left over. I draw 2 arrows going up and I put an oxygen on it. And then the 2 bonds on the less substituted carbon is just going to get hydrogen. So I literally just draw 2 more lines and put a hydrogen on there, or you can combine them together as CH3. That's okay. So if we look at this carbon, the more substituted carbon in my alkyne, is this carbon, the one that's attached to my double bonded oxygen. This carbon, the less substituted side, is this carbon. So we've gained 2 hydrogens. We went from CH to CH3. So this is not, it's kind of hard to make that transition, but I just remember both carbons gain 2 additional bonds. What do they go to? This one goes to 2 oxygens. This one goes to 2 hydrogens. I end up making a ketone now. So under Markovnikov addition to an alkyne, I make a ketone. So now I want to do the same thing, just like we did with the alkene. I want to be able to do the same thing, but anti-Markovnikov. When we did the anti-Markovnikov addition to our alkyne, we used hydroboration. So we used BH3. So we're going to do the same thing here, but we need to use a special reagent. So this is part of your list. We will talk about a lot of special reagents. This reagent is used for other things, but traditionally it's used to make this addition of an oxygen to an alkyne going anti-Markovnikov. So this molecule is called diazoyl borane, and it's a specific reagent. You don't need to know how to draw it, but you should know, if I show you this molecule, You should be able to call it diazomal borane. And I know that this reagent is specifically used for converting an alkyne to an aldehyde. And more importantly, we are adding an oxygen anti-Markovnikov now. So when we added an OH anti-Markovnikov to our alkene, we used borane. Here to add a oxygen anti-Markovnikov to our alkyne, we're using diazomal borane. So if you look, the reaction's kind of similar. So we use our borane compound. We still do the second step with the workup with hydrogen peroxide and sodium hydroxide, so that's the same thing. But the difference here is we are adding our oxygen anti-Markovnikov to the less substituted side. So here I have an alkyl group, more substituted side. This carbon's the more substituted side. This carbon is the less substituted side. So now this one is going to get my oxygen. When I take a terminal alkyne and do anti-Markovnikov addition, I end up making an aldehyde. So this carbon here is that carbon there. And we end up looking, so if we look at this reaction, I go from reactants to products, it's the same idea that we just did. It's just flipped around. It's just going on to the other side. So when I look at this, the reagent tells me what's going on. When I see diazomal borane, that means I'm adding an oxygen anti-Markovnikov to an alkyne. So here's my alkyne. Anti-Markovnikov means it's going to go on the less substituted carbon. That's going to be the one with the hydrogen. Still the same process. We're breaking these two multiple bonds. So we break two bonds, and each carbon that was part of my alkene, my alkyne, gets two new bonds. And then the question is, what goes on those two bonds? Now the oxygen goes on the less substituted carbon, this one. So I gotta draw two lines going out, put an oxygen on there. That makes an aldehyde. So this carbon is this carbon in my product. So we still have a hydrogen left over. That's why we end up forming an aldehyde. So this terminal alkyne, this hydrogen transposes over here. So now the carbon on the more substituted side, it gains two hydrogens. So these two bonds, there's going to be two new bonds coming off of this carbon. What does it get? Two hydrogens. So here we had no hydrogens. In this product, we have two hydrogens. So the addition of diazomal borane to an alkyne does an anti-Markovnikov addition to the oxygen, and overall what we end up doing is forming a aldehyde. So here, the last thing, hydrogenation, it does exactly the same thing it did with an alkene. It turns it into an alkane. We completely get rid of all the multiple bonds and we replace them with hydrogen. The same thing is true. You use H2, literally hydrogen gas. You need a catalyst, nickel, palladium, or platinum. Doesn't really matter. And here what happens is you break the two bonds, and now same thing, we form two new bonds on each carbon. So we break the two pi bonds in here, and that means I'm going to be forming two new bonds on each carbon. And the question is, well, what goes on those new bonds? Hydrogen. Everything gets hydrogen here in this case. So if we look at it, this carbon is this carbon is this carbon right here. Instead of this CC double bond, what they're now doing is being bonded to hydrogen. So each carbon gains two new bonds, and every one of those bonds is going to hydrogen. So when I look at this, same thing, the reagent tells me what's going on. I see hydrogen and a transition metal catalyst here, nickel. I know I'm doing a hydrogenation, which means I need to get rid of the triple bond and end up with an alkane. So the way I look at this, both of these carbons, I break this double bond. Each carbon that was part of my alkene gets two single bonds. What goes on those? Hydrogen. So here, this carbon has one hydrogen. In the product, it has three hydrogen. It's gained two more. So this carbon is this carbon right here. This carbon has no hydrogens. During hydrogenation, it adds two hydrogens, so it becomes this carbon here. So overall, the actual steps are almost exactly the same as when we did hydrogenation to an alkene. And with this, overall, what we end up doing is doing the process twice. We add two hydrogens. So during this process, we're not going to talk about it a little bit. After we add the first hydrogen to an alkyne, we actually form an alkene, but the reaction doesn't stop. It further adds another hydrogen, and then we convert that alkene all the way to an alkane. So this addition to hydrogen actually happens twice, and we literally go through an alkene intermediate. And the idea is it would be nice if we could actually stop at that alkene intermediate. That means we could convert an alkyne to an alkene. If we could just add one hydrogen to our triple bond and then stop. So to do this, we use a special catalyst called Lindlar's catalyst. And what it's called is a poison catalyst. So it means it doesn't work as good as it normally would. And so Lindlar catalyst reacts with alkynes to make cis alkenes. And when we look at this, it kind of makes sense. So we have an alkyne, we reacted with hydrogen, but instead of our transition metal catalysts like nickel, palladium, palladium, we have Lindlar's catalyst, which it still contains a transition metal, but it's weakened such that we can't do the addition of 2 hydrogen molecules to our double bond. We can only add 1 hydrogen to our double bond. So here we're back to like a normal hydrogenation like we did with an alkene. We break 1 multiple bond, we form 2 single bonds. What goes on those 2 single bonds is a hydrogen. And we can see why this molecule forms cis, because we remember that the addition of hydrogen to a multiple bond is syn. So that means the 2 hydrogens that we put on to our triple bond here have to be on the same side. So here this hydrogen and this hydrogen are on the same side. That pushes these 2 R groups on the same side. That makes us have a cis double bond. So by that, cis means that the 2 carbons are on the same side and the 2 hydrogens are on the same side. And we do this because we only get 1 addition of hydrogen, and hydrogens add syn across a double bond, which means they have to be on the same side. So if we look at a real example here, same deal. All I have to do is break 1 bond. So I'm going to have a double bond remaining. I break 1 bond, that turns into 2 single bonds. What goes on those single bonds? A hydrogen and a hydrogen. And then I have to make sure that to be able to show that these hydrogens are on the same side of my multiple bond. And that pushes whatever alkyl groups we have here also to the same side of the multiple bond. So we form a cis double bond. So using Lindlar's catalyst, we're able to convert an alkyne to a cis alkene.